Notice that we've studied three different intermolecular forces. So we started off with Keesom, angle average dipole-dipole, and we saw that the potential was equal to a cluster of constants divided by r to the 6. The Debye interaction, which was dipole-induced dipole, we saw was equal to a cluster of constants divided by r to the 6th. And finally, the London interaction we saw was a cluster of constants divided by r to the 6th. So all of these forces can be put under one umbrella. We call them the van der Waals forces. So that's an inclusive term for all the different types of interactions you have, Keesom, Debye, and London. And because they all have this form, we can add them together and say that in general there's an attractive potential, the van der Waals potential, that is equal to some constant divided by r to the 6th. Now, how does this play out when we start to look at things bigger than molecules? What if we have two colloidal particles, each made up of trillions and trillions of atoms? How do we figure out the attraction between them? Well, if we think about it, this atom is going to have a van der Waals attraction with that atom. So we can figure out what that is just by using what we've already learned. Of course, there's more than one atom in here. So what we'd have to do is add up each interaction with that atom, with all the atoms in the other material. And we'd have to do that over all the atoms here. So it's really a double integral. Here, integrating over these, and then doing it for each atom on here. And then, of course, we divide by 2 because we just double counted. And if we do that, we come up with something called the Hamaker attraction. So all the Hamaker attraction is scaling up from an atomic or molecular world up to the macroscopic world, and all we're doing is adding up a bunch of different van der Waals attractions. So there really isn't something called the Hamaker attraction. All we're doing is looking at van der Waals attractions on a bigger scale. So whenever we're talking about nanoparticles or anything bigger than that, we're going to be saying Hamaker attraction, and when we're talking about molecules, we'll say the van der Waals attraction, but really it's the same thing. Well, it turns out that when you scale up over all those different atoms, add them up, it actually ends up making the force longer ranged. So there's two equations I'll show you. One is for infinite planes. So we have a block, material, separated from another block by a distance h. And the blocks, in theory, they're infinite, but this is actually a good approximation as long as their thickness is bigger than the separation here. So in this case, V, the attractive potential energy, is just negative H11, which is a constant that depends on what these materials are. So we're assuming this is a block made of material 1, and this is another block made of material 1, divided by 12 pi times this separation distance. Separation distance squared. So notice that we're actually relatively long ranged here. Unlike the microscopic van der Waals attraction, which dies off as r to the 6th, this dies off as distance squared. So it's relatively long ranged. The other situation I'll show you is if we have two spherical particles, also separated by a distance h. And notice in both these cases, this is the surface to surface distance. It is not the center to center distance. So if we have two spheres, each of radius r, both made of material 1, then the attraction between them is minus H11, the constant that describes the materials, the radius, and we divide by 12h. Notice the dimensionality of these two equations are different. This has a factor of h, This has a factor of 8 squared. What that means is that this is going to give you units of joules. Right? The Hamaker constant actually has units of joules, and so here the distances cancel, we get units of joules. This is energy per pair. And this has energy divided by meters squared, so this is going to be energy per meter squared. So the bigger the plates, the stronger the energy of attraction.